Martin, this is the import-export exercise.
The
So
next way.
the way it works is we're going to give each other things that we're thinking about, right? And then we're
Well,
going to
or like big ideas, big concepts
big
that we're
ideas,
interested in
but something
exploring.
that we sort of know to some degree.
Yeah, of course, of
Right.
course. It's something that we like to think about.
Yeah. So
Okay,
I
so
I I think the one thing I like to think about, as we talked earlier, is logical puzzles, because it's something about the way my brain works, like just in logical puzzles, it could also be, in a sense, like writing an equation and modeling. So this kind of quantitative thinking. How about
okay.
you?
I like to understand biological systems based on first principles. When I say first principles, what I mean is the underlying physics and chemistry. Right. So that's
Like
what I mean.
underlying, because that's at the
Yeah, exactly. But I
backbone.
want to
So,
understand the system by saying, okay, based on this physics and this chemistry, this is actually the optimal solution that biology can come up with
okay.
under certain constraints, right?
Okay.
But sort of try to understand why is it like this based on the physics and the chemistry that's going on.
Okay. I got one. Adaptive systems. Adaptive systems. So by this I mean a system that's able to learn, essentially, that without a program, on the fly, it can find, explore a solution and then stabilize.
Okay. I'm tempted to put natural selection, but I know that's also something that you like to think about.
No. I mean, it should be something that we do think is like unique, sort of like more me, more you.
Well, when I say natural selection, really what I mean is optimization,
Okay.
right? So
Optimization. Say a little bit more about that.
So basically the idea is to think about, given on what we know about what the system is, what is the objective function of the system? Like what determines the selection pressure? To think about, what would be the optimal solution that should be accessible to this organism, that this organism could evolve to, right? So that basically we set the boundary conditions, and then we ask what is the optimal solution, with the idea that reality should have evolved to something similar to what is optimal based on what we understand about the system.
Okay. One thing that I like is, it's going to seem really banal, but it's a good time course, because in a time course, you are able to find causality, or at least a hint of causality, because while, of course, correlation does not necessarily mean causation, if you do have a causal mechanism, then, and it's not reflected in the correlations that you see, you should rule it out, because a causal aspect. So I think there's something about time course that really helps you to figure out a system. What about you?
Okay. Well, actually,
You got that devious smile.
I'm more about steady state.
Oh yeah, you're more like a homeostasis kind of a guy.
Yeah.
Steady,
because
as she goes. Steady state.
Because if you like time course, that just adds another dimension that makes things even more complicated than they are anyway. So I'm more thinking of stable systems. But now we have very abstract principles.
Well, yeah, what do we do with them?
Which is, instead of could have been something much more concrete, right? You could have written transcriptomics, for example.
It's a little vague, but we're going to work with this.
No, but maybe that's actually what makes it interesting. Right?
Okay.
We now find some project where we could apply these different.
So I should try to import something from you, and you need to try to import something from me into your world, right?
Well, we find some project that would be some middle ground.
I wonder if, when you think about optimization, it can be framed as a logical puzzle.
Well, your adaptive systems are optimizing. Right? That's what learning really means.
Right.
Like
you get the feedback, and you're trying to minimize some cost.
Exactly. So those two things are pretty close to each other, actually, I think.
But optimization, are there concepts involved in the whole field of optimization that you can think of? Like maybe, so tell me more about optimization.
Of course, there are different algorithms that you can use to find the optimal solution or to
Hmm.
move towards the optimal solution. And I'm kind of wondering if,
Hmm.
if the
Like a
optimal solution
gradient
is a steady
descent.
state, right? Something, converges to, some local optimum.
Mm-hmm.
You could look at the time course
Mm-hmm.
of how you get there, right? So
Well, you're really trying to check off all the boxes.
yeah,
Um,
let's just try to see if we can come up with a project that could combine that, right? So,
okay.
earlier you were talking about this AP1 system, right? And
Right.
you said you want to do an experiment where you start in one state, right? And then you change the environment
And it goes
and it adapts to a new well, it moves to a new state that is
achieving a steady state there.
right. So that's kind of,
So it's like in a steady
combining
state,
all of these things. Yeah,
learning back to a steady state.
exactly. So this is already actually combining a lot of
But
these
but
ideas.
yeah, but what is the actual insight? Because what is it? What is the thing about a steady state? What are some characteristics of it? Something we can measure? Is it a low variability setting? Is it dynamics that are different? What is it about steady state that you like?
Just the fact that it's easier to understand than a dynamic state, right? That's the only reason I like it.
What does that mean? Easier to understand?
It means you have one dimension less. You don't have to worry about
There's
time.
no time.
There's no time. Right?
It,
You're
ma- it
asking what?
maintains itself. It's stable.
Yeah. So basically, you're asking at when it had time to adapt, when it
So
had infinite time to adapt, right? What would be the state?
so if there was some kind of uh, network or whatever that underpins it, it would be something that turns something on, and then that something somehow stabilizes it. But it's something it's actively maintaining the steady state, right? It's not like it's doing nothing.
Yeah. Yeah.
It's not that it's
Yeah.
doing nothing. It's just it's reached some kind of equilibrium where
Yeah.
the forces from one to the other are matched. Right? There's some kind of matching that happens. Can we use that?
Sure. Sure. How do you want to use that? For what do you want to use that? Should we stay with the AP1 example, or should we look
Sure.
at another
Yeah.
system?
I mean, I'm fine with talking about AP1 all day.
Okay.
So here, if we're staying with AP1, it's that these dimers are somehow also taking care of maintaining themselves, maintaining their own presence, stabilizing and inducing more copies of themselves. But what may look to us like steady state is really, what I'm trying to say is like at their level is a whole act. It's actually, it seems like nothing's happening, but there are little minute movements that are keeping things in check.
So you're saying that the system is basically wiggling around
Yeah, that's the
at the
hypothesis.
optimal point, right? So it's sort of
Yeah,
trying to move all the time and just moves back because it already is at the optimum.
yeah. What if we formulate a hypothesis? This is our hypothesis that really the way adaptive systems work is that there's this time course, large scale changes,
Mhm.
and then the system stabilizes, but it doesn't actually turn itself off, but rather the changes become smaller, so small you hardly even see them, but they're there and they're crucial for keeping it in check and in that state. What do you think? I wouldn't have thought of that. It's a good hypothesis that came from this.
Okay.
I think we
Yeah.
need to think about it. Thank
Yeah.
you.
Thank you. It's just that I don't think we really combined our
Why? Look,
ideas,
steady
did we?
state and adaptive. Well, I think we did.
Okay. Did we? Did we though?
All that's required is an interesting conversation, right? Yeah. Okay, good.